Have you ever really thought about what's going on when you ride a bike? I mean, it feels so simple, right? You pedal and you move forward, but underneath that super simple feeling is this incredible dance of physics. It's like a conversation happening between the gears, the chain, and the wheels. Today, we're going to decode that conversation. We're going to uncover the hidden math that turns your effort into pure speed. And believe me, this isn't just about bikes. This is the physics behind pretty much anything that spins and moves. Okay, so let's jump right in with a very specific puzzle. I want you to picture this bike. The front gear, the one you pedal, has a 5-inch radius. The little gear on the back wheel, that's got a 3-inch radius. And the tire itself is pretty big, with a 17-inch radius. Now, if you pedal just fast enough to make that big front gear spin exactly once every second, how fast is the bike actually moving down the road? How in the world do we get from a simple spin per second all the way to a speed we recognize, like miles per hour? It feels like a massive leap, I know, but stick with me. We're going to build the bridge to get to that answer. So, I want you to think of this as a kind of puzzle box. We have all the pieces right here in front of us, but they're not speaking the same language. We've got spins, we've got inches, and the answer we want is in miles per hour. To unlock this whole thing, we just need a couple of special tools to help us translate between all these different ideas. And this right here is the heart of the challenge. You've got the pedal gear spinning. That's a circular motion, right? That spinning motion gets transferred to the chain, which moves in a straight line. That's linear motion. Then that chain makes the back gear and the tire spin all over again. We're back to circular motion. So you've got 3 different parts, 3 different sizes, and this constant switch between spinning around and moving straight ahead. It's a fantastic little physics engine when you really look at it. So, what's our first tool for cracking this code? It's something called dimensional analysis. I know, it sounds a little fancy, but trust me, this is your secret weapon. It's the key that lets us translate inches into miles and seconds into hours. It's how we're going to get all our pieces to finally speak the same language. So what is it, really? Well, it's just a super clever way of multiplying by the number 1 over and over again. Think about it. A conversion factor, like 12 inches per 1 foot, is really just a fraction that equals 1, because the top and the bottom are the exact same length. By strategically multiplying by these special ones, we can cancel out the units we don't want and end up with the ones we do. It's actually really elegant and incredibly powerful. And here's the recipe for it. It's a simple 4-step process that works every single time. 1. You start with what you know. 2. You multiply it by a conversion fraction. 3, and this is the crucial part, you always put the unit you're trying to get rid of on the bottom of that fraction. That way, it cancels out. And 4, you just cancel the units, do the math, and you're done. Let's just see it in action real quick. Say we want to turn 3 miles into inches. Okay, we start with 3 miles. First, we need to get rid of miles. So we multiply by 5,280 feet over 1 mile. See? Miles is on top and on the bottom, so poof, they cancel out. Now we're left with feet. So we do it again. We multiply by 12 inches over 1 foot. Feet cancel out, and we're left with exactly what we wanted, inches. Simple, right? Okay, tool number 1 is officially in the bag. Now for our second big idea. This one is all about the difference between just spinning in place and actually going somewhere. This is the concept of angular speed versus linear speed, and it is at the absolute heart of how a bike works. This slide lays out the difference perfectly. On the left, you've got angular speed. Just think of that as spin speed, like revolutions per minute. Every single point on a spinning record, whether it's near the center or way out at the edge, completes a full circle in the exact same amount of time. Their angular speed is identical. But on the right, we have linear speed. This is how fast a point is actually traveling through space. A point near the center is moving kind of slowly, but a point on the outer edge has to travel a much bigger circle in that same amount of time, so it has to move much, much faster. And this quote from our source material just nails it. Go back to that old vinyl record spinning. A little speck of dust near the center label is barely moving, right? It's just making a tiny little circle. But a speck on the outer edge, it's whipping around, covering this huge distance in the exact same amount of time. So they have the same spin rate, the same angular speed, but a way, way higher linear speed out on the edge. That's the key to everything. All right, we've got our tools, we've got dimensional analysis for converting our units, and we understand the difference between spinning speed and moving speed. It is time to go back to our bike. Let's assemble all the pieces and solve this thing step by step. Okay, step 1, the pedals.
So remember, our front gear has that 5-inch radius, and it's spinning at 1 revolution per second. That's its angular speed. The very edge of that gear, where the chain is sitting, is traveling in a big circle. Its linear speed is simply the circumference of that circle, which works out to about 31.4 inches every single second. And because the chain is attached, the chain has to be moving at 31.4 inches per second. Boom, we've just translated angular speed into linear speed. Now that chain, which is moving along, grabs the smaller 3-inch gear in the back. So here we're doing the exact reverse. We're converting linear speed back to angular speed. The chain is pulling at 31.4 inches per second on a gear with a much smaller circumference. What does that mean? It means that little gear has to spin a lot faster just to keep up. It works out to about 1.67 revolutions per second. And since that gear is bolted directly to the wheel, the entire wheel is also spinning at 1.67 revolutions per second. And for our final step, we look at that big 17-inch tire. We know its angular speed, right? It's 1.67 revolutions per second. So to get the bike's actual linear speed, we just need the tire's circumference, which is a whopping 107 inches around. So for every single spin, the bike lurches forward 107 inches. At 1.67 spins per second, that's about 178 inches per second. Now we just pull out our secret weapon, dimensional analysis, to turn that into something we can understand. We'll convert inches per second to feet per second, then feet per second to miles per hour. And after all of that, after all those conversions, from the pedals spin to the chain speed, from the chain speed to the wheels spin, and from the wheels spin to the bike's speed, and then finally converting all those inches per second, we get our answer. That one simple pedal revolution every second translates to a speed of just over 10 miles per hour. The puzzle is officially solved. But here's the really cool thing. This isn't just about bikes. These exact principles, angular speed, linear speed, the importance of the radius, they are absolutely everywhere. Once you see it, you can't unsee it. You'll find it in running tracks, car tires, even the planets themselves. For instance, take a running track. Ever wonder why the starting lines are staggered for races that go around the curve? It's because of this exact principle. Even though the runner in the outer lane has the same angular speed, they make the turn in the same amount of time, their radius is larger. Over 4 laps, that tiny 2-meter difference in radius means they actually have to run an extra 50 meters. That's why their starting line is way up ahead. Or hey, think about your car. We talk about its speed in miles per hour. That's a linear speed. But to make that happen, the tires have to be spinning at a very specific rate. This question just flips our bike problem completely around. If you know the linear speed and you know the tire size, you can work backwards to calculate the angular speed. In this case, the revolutions per minute. It's the exact same physics, just in reverse. So what are the big things to take away from all this? First, dimensional analysis isn't just for bikes. It is your universal translator for any kind of unit. Second, there's a direct, unbreakable link between spinning speed and moving speed, and the key that connects them is always the radius. Third, bigger radius always means more linear speed for the exact same rate of spin. And finally, as we saw with that running track, even small differences in size can have a huge impact on speed and distance. So I'll leave you with this final thought to chew on. At the equator, because of the Earth's massive radius, the surface is moving at over 1,000 miles per hour. That is an unbelievable linear speed. So why don't we all just fly off into space? Well, the answer lies in the very same principles of motion and reference frames we've been talking about today, just on a planetary scale. It's something to think about the next time you feel like you're standing perfectly still. Thanks for joining this explainer.